Welcome back to Chemical Reactor Design. We are now in lecture 12, the continuation of chapter 3. Last time we have derived together a rate law for this reversible reaction, which symbolically we wrote it as 2B produces D plus hydrogen. And the rate law was found to be this. Okay, and we have also defined Kc to be the concentration of the product D at equilibrium times the concentration of hydrogen at equilibrium divided the concentration of benzene at equilibrium raised to the power 2. This is the expression of Kc, which is used in this rate law. And we have also asked about where we're going to find the values of Kb and Kc from. So we said for Kb we need the knowledge of kinetics to find the value of the reaction rate constant. And regarding Kc, we said we need the knowledge of thermodynamics, and basically we will find it through first finding the value of K, the equilibrium constant. So let's take a short trip to the thermodynamics world. In thermodynamics, you have seen this figure, which is ln K versus 1 over T. This is where you find the value of K, equilibrium constant. Of course, you can also calculate the value of K through using the expression ln K equals minus standard delta G reaction over RT. Anyway, so let's look for our reaction, which was the dissociation of benzene into diphenyl and hydrogen. And here we go. Here it is. This is the reaction. However, it's written in different stoichiometry, as you can see. It's here per 1 mole of B. Okay. So we can find the value of Kc using this figure. The first thing we need to know is the temperature of the system, so that we can calculate 1 over T. For a given value of 1 over T, we can basically go to that value. For example, here, go all the way to the curve here, to the straight line, and then read the value of ln K. Once we find the value of ln K, basically we can calculate the value of K, and then of course there are relationships between K and Kc, which are found in the thermodynamics review. If you go to these slides, you will find all the different relationships between K and Kp, K and Kc for the different cases. However, this value of Kc that we just calculated is for this reaction, correct? And for this reaction, you know that the expression of Kc is simply the concentration of D at equilibrium raised to the power half times the concentration of hydrogen at equilibrium raised to the power half divided by the concentration of B at equilibrium, as you can see from this expression. This is the expression of Kc according to the reaction written in this stoichiometry. The issue is that in our rate law, the Kc expression is given by this equation. So now, can we find the value of Kc at a given temperature from the value of Kc that we have just found from the figure? course we can. And if you compare these two equations, you can easily see that Kc, the one we are using in our rate law, basically equals the value of Kc that you find from the figure raised to the power 2. Basically, if you take this expression and raise it to the power 2, we end up with this expression, which expresses the value of Kc used in this rate law. So for instance, from the figure, at a given temperature, we found that the value of Kc equals to 2, then the value of Kc in our rate law will simply be 4. Okay, so let's go back to the world of kinetics. Let's have some final remarks regarding the rate law. At equilibrium, the rate of reaction is identically 0 for all species. You know that already. The net rate of formation of B is 0 at equilibrium because the rate at which B is consumed through the forward reaction equals the rate at which B is produced through the reverse reaction. The same is correct if we talk about D, diphenyl. The net rate of formation of D is 0 at equilibrium. All rate laws for reversible reactions must reduce to the thermodynamic relationship relating the reacting species concentration at equilibrium. Meaning, if we take this rate law and we say at equilibrium, obviously minus Rb equals to 0, and then we solve for Kc, we get this expression, and this is a valid expression for Kc, looking at, for instance, this stoichiometry. So that's what meant by this point. If we perform this step and then we find an expression for Kc which is wrong, then that means the developed rate law is wrong. For instance, if by doing this step we find that Kc equals Cd at equilibrium to the power 2 times Ch2 at equilibrium divided by Cb at equilibrium to the power 2, then we know that this expression is wrong. Okay, let's go to the reaction rate constant. The reaction rate constant K is not truly a constant. It is merely not function of concentration. The quantity K is referred to as either the specific reaction rate or the rate constant. It is almost always strongly dependent on temperature. It depends on whether or not a catalyst is present. So if you have a very good catalyst, the rate of reaction will be faster. That means the value of K is bigger. In gas phase reactions, K may be a function of pressure, maybe. In liquid systems, it can also be a function of the ionic strength of the solution or the solvent type. The last two variables, meaning the solvent type and the pressure, normally exhibit much less effect on K than T does, with the exception of supercritical solvents. This assumption is valid in most laboratory and industrial reactions and seem to work quite well, which is K being a very strong function of T. It was the great Swedish chemist Arrhenius who first suggested that the temperature dependence of Ka, the rate constant, could be correlated by this relationship, which you are all familiar with, where A is the pre-exponential factor or the frequency factor, E is the activation energy, R is the gas constant, and T is the absolute temperature. Arrhenius equation has been verified empirically to give the temperature behavior of most reaction rate constants with an experimental accuracy over fairly large temperature range. So it's really a good equation. The Arrhenius equation is derived in the collision theory section on the CD-ROM. A is the pre-exponential factor or frequency factor. So this is the A here. Or you guys know it as Arrhenius constant. So let's look at this reaction. A reacting with BC to form AB and C. And in order for the reactants to go from here to here, it will first go through an activated species, as you can see. So here the reactants are, these are the product, and in order for these guys to go to here, it first has to go through an activated state species. So it is A, in fact, is the decay rate to the products. So it's the rate at which this activated species will decay to the product, and is function of the lifetime of the activated species and the likelihood that it will convert to a product instead of back to a reactant. So if the lifetime of this intermediate is very large, so when A collides with BC and it forms this activated species or activated intermediate, and the lifetime of this activated species is long, that means it's very stable, it stays for a very long time, that means the rate of reaction would be slow. And where can you see that? You can see it in the value of A. The value of A will be small. And A is also a function of the likelihood, the possibility, the probability that this species will dissociate into the product rather than dissociating back to the reactants again. So now we know what A reflects. Again, it's called the decay rate to the products, the decay rate of the activated species. Okay, let's talk about E now, the activation energy. Why there is an activation energy? If the reactants are free radicals that essentially react immediately on collision, there usually isn't any activation energy. However, for most atoms and molecules undergoing reactions, there is an activation energy. A couple of the reasons are that in order to react, in order for A to react with BC, for instance, steric and electron repulsion forces must be overcome as the reacting molecules come close together. So if A is reacting with BC, first the system has to overcome the repulsion forces. Where are these repulsion forces coming from? Basically could be coming from the shape of the molecule. For instance, methane. You all guys know that methane has a specific shape, right? So if you recall, just something like that, and then maybe you can plot. And then you have here hydrogen, another. So if the other reactant has to attack carbon from this side, first it has to overcome the steric repulsion forces. For instance, has to take the hydrogen and these two hydrogen away from each other, so there would be some space for the other molecule to attack the carbon. And not only that, you know all that atoms are surrounded by electrons, and also the same story is true for the other reactant. So in order for the two molecules to come close to each other, they have to overcome the electron repulsion forces. So all of this needs energy. You need energy from the system to make this happen, which is the both molecules come near to each other to react. The other reason is that the molecules need energy to distort or stretch their bonds so that they break them before forming new bonds. So again, if let's say this is the carbon as attached to another carbon, and there is the hydrogen attached to this. So if this part of the molecule will need to be detached so that the other molecule can attack this carbon and react with it. So first you need to distort and stretch this bond and then break it, and all of this needs energy. So energy needs to be supplied to distort or stretch this bond and then break it. So all of these energies required to overcome the steric electron repulsion forces and to break the old bonds and to form later on new bond, all of these needs energy, and this energy is known as the activation energy. Okay. So the activation energy can be thought of as a barrier to energy transfer from the kinetic energy to the potential energy. As you know, A is moving with a given kinetic energy, BC is moving in the solution as a kinetic energy. So when they collide, this and they form ABC, the intermediate, all this kinetic energy is changed to a potential energy. Now all of this energy is stored inside, and the difference between the energy here and energy here is known as the activation energy. So again, the activation energy can be thought of as a barrier to energy transfer from the kinetic energy to the potential energy between reacting molecules that must be overcome. Let's look at this term now, e to the power minus e over RT. The term e to the power minus e over RT represents the probability that a reactant species will find itself in the activated state. So what are the chances, what are the probabilities that these guys will form this guy? Well, the probability is calculated through this portion of the equation, and obviously this possibility increases as the temperature increases, because if you have high temperature, that means the kinetic energy of A is high, the kinetic energy of BC is high, so there are more chances that a collision between these molecules would have enough energy to overcome the steric and the electron repulsion and to distort the bond between B and C in order to form this activated species. So therefore, the higher the temperature, the larger the value of this term, and you can mathematically prove it. Okay, how else does the possibility of this term, or the possibility of having activated state molecule, could be high? The other case is when the value of E is very small. So as the value of E is very small, the activation energy is small, there are more chances that these guys can form the activated state, and also you can follow it up mathematically. Let's now look at the activation energy and try to explain it by collision theory. The energy of the individual molecules falls within a distribution of energies where some molecules have more energy than others. So you already know that the molecules are moving in a given solution, in a given system. So they are moving at a given energy, but these molecules do not all have the same amount of energy. Some molecules have more energy, some molecules have less energy. One such distribution is shown in this figure, the distribution of the energy, where F, which is the energy distribution function, and it's a function of a given energy, amount of energy, and the temperature of the system. So where F is the energy distribution function for the kinetic energies of the reacting molecules at different temperature. So let's see. Let's assume we have a system of A and B, or for simplification, let's just say A, where A is a reactant and B is a product. So let's look at the energy distribution for this given system, which has A molecules. Let's see. Assume that the system is at this temperature, 300 Kelvin. So you can see that the majority of the molecules have energy between 5 and 6 kilocalorie in this case. So the fraction of collisions with energies between 5 and 6 kilocalorie is approximately, so how do you find this fraction? Simply, it is an area under the curve between 5 and 6 kilocalories. How do you find it? It's the width here, 6 minus 5, times the height, which is around 0.083, which is the fraction of the molecules which have certain given energy, and can be found again by the height times the width. So here we go. That is 8.3% of the molecular collisions have energies between 5 and 6 kilocalorie. So now we understand what these curves mean, and I believe you have seen such figure in statistics in the statistics course. Okay, let's increase the temperature of the system. Let's increase it to 500 Kelvin. You can see that the energy distribution now changes. Now you can see that now the majority of the molecules have energy somewhere between 20 and 21 kilocalorie. And this is normal because you have increased the temperature. Therefore, the energy of the system has increased. And now the majority of the molecules have energy between 20 and 21 kilocalorie, as opposed to their energies when the system was at 300 Kelvin, which was somewhere between 5 and 6. Okay, now let's see. F for a given reaction, the activation energy was 30 kilocalorie. We want to find the portion of the molecules, or let's talk about reaction now. The portion of the molecular collisions, the portion of the molecules who have energy above 30 kilocalorie. Let's calculate that. Okay, so we are interested to know the portion of the collisions between the molecules who have energy higher than 30 kilocalorie. And suppose this is my activation energy of the reaction. That means if a collision possesses energy of 30 kilocalorie or more, then the reacting molecules can go to the activated state. Of course, if it doesn't have this much energy, it cannot reach the activated state. So if the system was at 300 Kelvin, the portion of the molecules who have energy 30 kilocalorie and above is only this portion. However, when I increase the temperature of the system to 500 Kelvin, this portion increases. As you can see, the area under the curve is much higher now. So this is the fraction of collisions at T2, 500 Kelvin, that have energy which is equals to 30 kilocalorie or greater. So now you can understand the relationship between temperature and the possibility of having reaction. Okay, so in conclusion, for this reaction, where A is reacting with BC to form an intermediate compound, and then this intermediate compound is dissociating into the product. The rate law is written as K, this is K, multiply by, let's see, this is K, multiply by the concentration of the reactant. Concentration of A times the concentration of BC, assuming that this reaction is an elementary reaction. So basically, the rate of reaction is a game of probability. Therefore, how can we quantify this probability? We can quantify it through the rate law. So minus RA equals A, which is the decay rate of the activated species, to the product, and obviously it's function of the lifetime of this activated species times the probability of this activated species dissociating into the product rather than dissociating back into the reactants, multiply by e to the power minus e over RT, which is the probability of finding the activated species, that probability of converting this into this. The probability of converting this into this depends on two things: the value of the activation energy and the temperature of the system. There we go. This and this. The smaller the activation energy, the more possibility that you have these guys converting to this guy. The higher the temperature of the system, the more collision that you have, which have energy higher than the activation energy. So the portion of these collisions will be more as the temperature of the system is more, and therefore this value will be higher. Okay, what else? How can we increase the possibility of the collision between A and BC? Obviously, we can increase the possibility of collision by increasing the concentration. So, therefore, that's why the rate of reaction is function of concentration, because higher concentration of A raised to the power 1, since the collision has to be between one molecule of A and one molecule of BC. So, the higher the concentration of A and the higher concentration of BC, the more chances for collision, and therefore the higher the rate of the reaction. Okay, how is the activation energy determined? Obviously, through the Arrhenius equation. You can take the ln of both sides and you end up with this. Then you can say, let's plot ln K versus 1 over T. That means you have to run the reaction at different temperatures and then calculate the value of K every time, and then you can plot ln K, this is ln K, or K on a logarithmic scale, versus 1 over T, and then you'll get a straight line, and then the slope obviously is minus E over R, and the intercept is ln A. So this is how you find the value of the activation energy. In literature, the value of K for a specific reaction is reported at a specific temperature along with its activation value. What if I need K at another temperature? That's simple. So I use this equation twice. First I write it for the case reported in the literature, then I write it again for the case where I'm looking to find the new value of K at this different temperature, and then you divide these two equations on each other, and then you rearrange to find this equation. So now I can calculate the value of K at any temperature T2 by having the value of K at a reference temperature T1 and the value of activation energy. Comment on K as a function of T. The rate of reaction increases with the increase of temperature. You know that already. Higher T, higher rate constant, and therefore higher rate of reaction. Okay, let's use the following equation to calculate the ratio K at 310 to the value of K at 300 for different reactions, meaning for different activation energies. So all what we have to do is plug in the value of E here, and then T1 is 300, T2 is 310, and then we are able to calculate K over K1. And let's see, for this reaction, this is the activation energy, for this reaction, this is the activation energy, and so on. And as you can see, the larger the activation energy, the more temperature sensitive is the rate of reaction. So you can see the ratio here is different, and actually the ratio increases as the activation energy increases. That means that reactions with higher activation energies more sensitive to temperature. So in all the cases here, for all the reactions, I'm increasing the temperature from 300 to 310. But for this reaction, which has the highest value of activation energy, the value of K increases by 13 times, more than 13 times, for the given increase in temperature, which is from 300 to 310. And why is that? We can go back and check the figure of the distribution, energy distribution function, and explain this. Okay, so make sure that you complete the set of the suggested problems, which is set number 3, and then come back again to listen to more lectures. Okay, with this I conclude my lecture today, wishing you all the best.